Hello, my name is Boyang Wu. My the ID is the 5454127, and here's my student ID card. And here's my final submission of the experiment. So, what are the Kepler's laws? The Kepler's law describes the motion of planet around the sun, and they are key to understand the orbital mechanics. Here's a breakdown of each law in simple terms. The first one is first law, the law of ellipsis. A planet orbits the sun in an elliptical path, with the sun located at one or two focal points of the ellipse. This means that the distance between a planet and the sun changes as it orbits. The second law is law of equal areas. As planet moves around its orbit, it swaps out the equal areas in equal times. This means that when a planet is closer to the sun, it moves faster, and when it's farther away, it moves slower. This keeps the swept area equal every time over time. The third law is law of harmonies. The time a planet takes to complete one orbit, its orbital period, is related to its distance from the sun. Specifically, the square of a planet's orbital third is proportional to the cube of its average distance from the sun. So, planet farther away from the sun takes much longer to complete an orbit. For here are my answers for question 9. For question A, yes, it does. Even though the trajectory of the move is small, it will still move. Question B, for the scenario 1, since it's about sun and Earth, the center of the mass is near the sun. For scenario 4, it is similar, although it changes the mass compared to the sun is still insufficient, and the answer should be same as question 1. The center of mass is near the sun. For scenario 7, the sun masses decreases, and the center of mass will be a little further away from the sun. For the answer for question C, in a planet-moon system, the center of mass is often located closer to or even outside the planet due to the smaller mass difference, resulting in more noticeable mutual orbits. In a sun-planet system, the center of mass is very close to sun's center due to its mass, causing only minimal movement of the sun around this point. This distinction affects the orbital passes, stability, and even the gravitational effects experienced by each body in the system. For the answers to question 11, since this is the distance between the Earth and the Sun, and the distance is labeled as 2 grid units, we can deduce that it is 1 AU, the average distance from the Earth to Sun. Thus, if 2 grid units are equal to 1 AU, so the distance between each grid marker is 0.5 AU. Here are my results, the screenshots for the results and the charts for the results. And here I did some calculations since I got the AU, so I can get the radius. Here are some further calculus about regarding to Kepler's third law. And as we can see in the results, these values are not entirely constant but closer, suggesting this radius might be intended to approximate the semi-major axis. However, it is still very enough to suggest either measurement in accuracy or approximation in the data. In an ideal Kepler system, these values should be nearly constant for a planet orbiting the same star. But here they show some variation. This could be due to the simplifications or the limitations in the simulation data. So for question 15, the planet with the fast orbital velocity is Mercury. This is because Mercury is the closest planet to the Sun, and the planets that orbit closer to the Sun travel faster. For question B, the planet with slowest orbital velocity is Neptune. The farthest recognized planet from the Sun in our solar system. Since it's so far from the Sun, it travels more slowly along its orbit. And for the reason for this is the difference in the orbit velocities is primarily due to the gravitational force exerted by the Sun on the planets, combined with Kepler's second law and Newton's law of universal gravitation. So, in summary, closer planets like Mercury have stronger gravitational pull from the Sun and requires a faster orbit velocity to remain in its orbit. And further planets like Neptune have weaker gravitational pull and thus move at a slower orbital velocity. So what did I learn in this experiment is that I learned about relationships between orbital distance and orbital period as described by Kepler's law. By analyzing the center of mass in both sun planet and planet moon systems, I observed how mass differences affect orbital velocity and stability. The experiment highlighted the closer objects orbit faster due to stronger gravitational forces, and it illustrated the differing dynamics in systems and with varying mass radius, like the sun planet versus planet moon scenarios. Thank you.